Hi, I'm Ben-Yaakov. This presentation is entitled How to Get the Energy Related Capacitance. Let me start off with explaining what is the problem that I'm trying to solve and explain how to deal with. If we have a MOSFET, there's always an output capacitance. Now, if the voltage across the MOSFET when it is off is high, this capacitance is charged, and then when the transistor will be turned on, the energy of this capacitance will be dumped into the transistor, causing, of course, a loss, and this is part of the switching losses of the transistor. Now, the total power loss will be this energy times the switching frequency. Now, the simplistic way of estimating this energy by the classical equation of capacitance times V squared over 2 is incorrect in general because here we have a nonlinear capacitor and the capacitance is changing while the capacitor is being charged or discharged. And consequently, if you like to use an equation of this form, you need to have this energy related capacitance as the equivalent capacitance related to the energy. This energy related capacitance is voltage dependent. For each voltage that the capacitance is charged, it's a different number. And then you can multiply it by V squared over 2. So the question how to get this energy related capacitance, and this is the subject matter of this presentation, and also how to get, of course, the energy stored in this capacitor. I'm showing here a data sheet of a MOSFET, silicon MOSFET, a hefty MOSFET, super junction transistor. It's a 650 volt, 30 amp, and the RDS is specified to 99 milliohm. And in recent years, we find that manufacturers are aware of this issue of energy related capacitance, and we can see now in recent data sheets some information related to it. For example, here we have this energy related output capacitance, which is this capacitance I was talking about, but this is one point. This is charging the output from 0 to 400. It will store energy, and you can calculate the energy by C V squared over 2, but the C you have to use is this 77 picofarad. Okay, so this is now available in most data sheets. Now, the classical information about capacitances are these plots. These are small signal differential capacitances. They are measured at different voltages at 1 megahertz, as a matter of fact, with small signal. Okay, so it's a small signal capacitance, call it differential or derivative capacitances. And we are interested in this particular one, and you can see that it is changing quite a bit from about, this is picofarad, so this is about 25 nanofarad down to maybe 70 picofarad. So the change is really very large, but this is not a capacitance you can use for calculating stored energy. For that, you need this energy related capacitance. And now the manufacturers are actually giving this type of a plot, which is the energy now, it's not the capacitance, just the energy stored as a function of the voltage. And this is very useful, of course, because if you know to what voltage is the transistor being charged, then you know what is the energy stored in it. Now, once you know this energy, then you can look up this template, you might say, which is energy related capacitance times V squared over 2. And from this, you can actually get the energy related capacitance if you know the energy. And in this presentation, I'm going to show how you can get this plot from this classical presentation of the differential capacitances, and of course then how you can get this energy related capacitance. And here is another MOSFET. This is now a silicon carbide, supposed to be much faster, and indeed the input capacitances, if we look at them, are actually smaller. But it's really interesting that the output capacitance and the energy related capacitance, this is this value here, is not that much different. You see, this is given for 300 volt, The 77 that we have seen earlier, it was given for 400 volts. This capacitance is going down with voltage. So the difference is not that large between the silicon carbide and the superjunction transistor, which is kind of surprising as a matter of fact. And also, this vendor is also giving this classical differential or small signal capacitance, and also now this plot of energy stored as a function of the voltage across the output or across the capacitor. As an introduction to the methods, I'm going to show how to calculate this energy stored and energy related capacitance. We have to look at the nonlinear capacitor and understand what does it mean, the capacitance of a nonlinear capacitor. Now, the very basic information of a device that stores energy in a dielectric material is this Q as a function of V. In the case of a linear capacitor, it's going to be a straight line. In the case of a nonlinear capacitor, it's going to be some curved line. And now we can actually define a number of capacitances. The derivative small signal or differential capacitance is actually the slope at a given point. Now this, of course, value is changing from point to point. So this is the differential or small signal capacitance. The large signal capacitance or total capacitance is this charge divided by the total voltage. Okay, so this is this slope here. We can also define a AC capacitance. This is moving from one point to another like this, and this will be this slope here. And then we have this energy-related capacitances and energy stored in a nonlinear capacitor. The energy stored can be calculated by this equation. This is the integral of this small signal or differential capacitor times the voltage. This is the local charge, the Q, you might say. And then if you take the integral over the span of voltage from 0 to a given voltage, then this will give you energy. Now, once you have the energy again, you can sort of relate it to this template of CV squared over 2 and get from this energy-related capacity. So I'm going to show now how to deal with this issue to get the information we want by actually two methods using LT-SPICE simulation. The first one is, I'll call it mathematical, and basically it is using LT-SPICE to solve equation by behavioral dependent sources. Okay, so the idea here is the following. First of all, we have to generate the information about the capacitance, the small signal capacitance or the derivative capacitance, which is the information, the basic information which is given in datasheet. And we can import this information into a table and then create a voltage which is equal numerically to this capacitance. The point is that SPICE simulator can handle parameters like voltage and current during the simulation, but it cannot handle, say, capacitance, which is changing during the simulation. So what the trick that we are doing is we are sort of coding the capacitance into voltage, creating a voltage which is equal to numerically to the capacitance, so we can then handle it as a variable in the simulation. So the first stage is to generate this table and then to have this node which has a voltage equal numerically to the differential of small signal capacitance. Next, we have a ramp with it changing with time linearly. And then I can calculate the energy by taking this integral. I talked about it. This is the voltage which represents the capacitance, the small signal capacitance. Again, it's already coded into a voltage, times the voltage, which is okay. It's a parameter which is allowed. And then what is also possible is to take the integral of this product, the function of time integral. You can do that. And then once you get this information as a function of time, which is also a function of the voltage, because this is now linear, you can use this energy to calculate on the run as a function of the voltage, the energy related capacitance. And then, of course, you can plot this information as a function of voltage, which is again linearly related to time. Now, the first stage is to get this information into a table. So what I'm doing here, I'm looking at these points here and sort of digitizing it, getting the value and the voltage, voltage and value, etc., and putting it into the table of LT-SPICE. And here it is. Now, this is a behavioral voltage source, which is defined, the value is defined by a table. The input to the table is the voltage, which is the ramp. Here it is. And then this is the digitized value. This is the voltage, capacitance, etc., up to 600 volt. So this is the digitized value. And then once I have it, I can actually calculate the energy, which is the integral of the capacitance times the voltage. SDD is the LT-SPICE operator for integral. This is just a scaling factor. And so the voltage here will be energy, which we can then use in order to calculate the energy-related capacitance by this equation that I've shown earlier. So this is actually doing the math in LT-SPICE. So first thing I'm showing here, the matching of this table, or the fitting of the data to the table, and the actual data. You see the fitting is pretty good, except here the interpolation by LT-SPICE is not actually following this, so it's a little bit different, but in general it's a pretty good fit. You see that the value here is about the same, and also the value here, and I've checked all the other points, they are pretty good. So this is just the transfer of this data into a table. And then I've run it to get the energy. So this is the energy in the capacitor, the nonlinear capacitor that I've taken off the datasheet. And this is what the simulation is giving us, and this is from the datasheet, because this information is given in the datasheet. So as can be seen, that it's a very good fit. Say 400 volt, which is about here. We have 7 microjoule, and 400 volt again, we have here 7 microjoule. It is in fact identical to the data given in the datasheet. And here is now the energy related capacitance that has been calculated. And we see it starts at 20 nanofarad and then it goes down. Now it sort of resembles this curve here, which is the small signal or differential capacitance, but it's not the same, because this is actually related to the integral from 0 to this point, while here it's a local capacitance. So at the beginning it's about the same, of course, but if we go to say 100 volt, here we get 424 picofarad. This is the energy related capacitance. And here at 100 volt, we get about 70 picofarad, because this is the local one, while this is actually taking into account that energy is also stored in this larger capacitance, although the voltages are lower. So it's doing all the math here to get the actual equivalent capacity. Now in the data sheet, they have one point, I've shown it earlier, and that is for 400 volt. And the value is 77 picofarad in the datasheet. Here I'm getting 99 picofarad for the energy-related capacitance. Well, the difference could be, first of all, the question of how accurate is this table that I've generated. And also, I'm not sure that the data used by the manufacturer to get this number is the same data that I've used in order to generate this curve. There is a spread, of course, in this parameters. So in general, I think it's anyhow a good fit between what we got here, the simulation, and the data sheet. The second approach to do this extraction of the information of the energy and the energy-related capacitance is to use a model of the nonlinear capacitor. Now, if we have a nonlinear capacitor, we can express this relation between the current and the voltage by this, you might say, state equation. And here we have this differential or small signal capacitance, dV dt, which this expression can be emulated by a behavioral source defined by this equation. In empty spice, it will look something like this. This will be the voltage that represent the differential capacitance by the table as we have done before. And this is now an operator of LT spice for derivative. So it's taking the derivative of the voltage across this capacitance. So this is the capacitance. Once we have the current and the voltage, then the product of these two is the energy. Once we have the energy, we can of course calculate the energy related capacitance as before. And here is a empty spice schematic that I've built for this purpose. Now here we have the ramp first of all of the voltage. This is now the table. So the voltage here is the small signal or differential capacitance. Now here is the model of the nonlinear capacitor. Here is the current source defined by the voltage, which represent the differential or small signal capacitance, times the derivative of the voltage across, this is voltage here. This is a voltage source with zero voltage just for sensing the current. So this voltage here is actually the voltage on the capacitor, and this is just the derivative here. Once we have the voltage and the current into this model, then we can take the product to get the energy, okay? Voltage times current, the integral is the energy. So by this I can get the energy. Once I have this energy, I can of course calculate the energy related capacitance. So this voltage here represents the energy related capacitance. So here it is. Again, it's very good fit, very similar to the plot in the datasheet. And here I have the energy related capacitance. Again, also very similar to what we got before. It's practically the same. And now I can compare it to the datasheet again. And here we have again the 99 as compared to the 77 picofarad of the datasheet as I've shown before. And finally, let me show you an output of a Google AI when I asked how to do this calculation. And then it says to calculate the energy stored in a capacitor given differential capacitance, then you need to integrate the differential capacitance C with respect to voltage, this one here. Now this gives just the Q, the amount of charge. And then it says you take this amount of charge, multiply it by the voltage to get 1/2 to get the energy. This is incorrect. Or you take CV squared over 2, which is also incorrect because C has to be the energy related capacitance, which you don't have. So this whole thing is incorrect. This brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest and perhaps it will be useful to you in the future. Thank you very much.